And welcome back, everyone, to Beyond the Forecasts. I am Chief Meteorologist Michael Stevens, and I'm going to tell you this right now. I'm recording this earlier in the day, but my goodness gracious, it is muggy. It is above my comfort level here in northern Michigan. If you know anything about me, getting to 80 and above is just not for me. But regardless, it is a beautiful day out here. And if you want to get out and enjoy, great day to do so. Now, yesterday we told you about air quality as well as particulates in the atmosphere. Well, today we're going to talk about what happens when light starts impacting particulates or rain or water, and refraction and reflection. So today's episode is going to be about the bending of light. So meteorologist John Gross is first going to jump into rainbows and how we see them, how they're made, double rainbows. We're going to break that down for you. And then after that, I will break down sundogs and halos, why you see them, and just how they're formed, both around the moon and around the sun. And then at the end of the show, I'm going to take you into a fun experiment of refraction, how you can do this at home and how you can explain it to the little ones, or you could even do it at work and surprise your coworkers. Be like, see this? This is why this happened. So that is what's coming up on today's episode, bending of light. It'll be a fun one. But first up, this day in weather history. Now buckle up, this one's a lot of fun. This is wild. July 15th, 1987. All right, so I would have been turning 2 in a few months. Unseasonably cold temperatures struck the United States, including Houghton Lake. I'm not just throwing this in there. This was actually in the fun facts on the website, including Houghton Lake, which read 37 degrees. But regardless, the high temperature for the day in Michigan was 58 degrees in Flint, which was their coldest record high for July, or their coldest record high for the day. Yeah, something like that. But regardless, July 15th, 1987, it was 37 degrees at one point in Houghton Lake. That is nutty. Can you imagine waking up in the middle of July and being worried about frost? That's insane. I was too young to remember it, so thankfully I don't remember it. All right, trivia time. Yesterday we wanted to know, true or false, men are more likely to be struck by lightning compared to women. All right. This one's a little bit crazy, but yes, this is true, all right? So the CDC, yes, the CDC actually put out a report that men are actually more likely to be struck by lightning than women because of the activities and men just being men. No joke, that's what it says. You ever heard of Midwestern dad stuff? So like, if there's a storm coming, dads will sit out there on the porch or go be out there until the storm's like right on top of them. That's kind of the situation. Men are more likely to be out fishing, golfing, swimming, doing things in storms and not coming in time. So the CDC says men are more ample to get struck by lightning than women. Not anything to do with genetics or chromosomes or anything like that. It's just men being men. So there's your answer. Today, we want to know, what is the highest wind recorded in a tornado? Is it 200 miles per hour, 312 miles per hour, 412 miles per hour, or 335 miles per hour? QR code right there. Hit it with your phone. That'll take you where you can go to answer, and we will have the answer for you on tomorrow's episode of Beyond the Forecast. And little hint, this was recorded in 1999 in an Oklahoma tornado. So, but the answer will be given to you tomorrow. All right, weather word of today, of the day. Today, it is cumulonimbus. Yeah, it sounds like a crazy big word, but that is a type of cloud, a thunderstorm cloud. So cumulonimbus is the very tall clouds that have lightning, thunder, hail, usually associated with severe weather. How these are made is very strong updrafts. So usually, typically, cold front or cooler air is moving through, boosting that warm air up, and it goes higher, 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 higher. And the taller the cloud gets, usually the stronger or more severe the storm can be. And it goes 40, 50, 60,000 feet at times. Cumulonimbus. Bling! It's the ones that look like anvils. Kind of like a supercell. It makes eventually a supercell if it gets strong enough. So there you go. All right, viewer photo of the day. Now, also an amazing viewer photo of the day. These are not just chosen on the day that we do the show. In fact, these are laid out weeks in advance by Olivia, who does a wonderful job. It just so happened that I put the show together and we're talking about refraction and reflection. And believe it or not, just on the offhand, viewer photo of the day comes to us from Judy Murtaugh and fits with everything we're talking about today. Check this out. She sent in an amazing photo of a halo around the moon. And if you look closely, it's a double halo. So there's one little one around the moon and then a bigger one on the outside. And in fact, you can see where it's almost like moon dogs on the side. And don't worry, if you don't know what I'm talking about, you'll get all of the information on halos, sun dogs, rainbows, and refraction and reflection coming up in the rest of the show. But absolutely an amazing photo from Judy from there in Les Genoux. So thank you so much, Judy, for sending that in. And as always, thank you to Great Rooms for sponsoring viewer photo of the day. We do appreciate that. All right, let's send it over to meteorologist John Gross, who's going to break down rainbows, why you see rainbows, double rainbows, how this happens. We're going to have all of that coming up right after the break.
Hey there, everybody. Meteorologist John Gross. Welcome back to Beyond the Forecast. Today's topic is brought to you by a viewer named Kathleen, sending in a question to me about a photo that she recently saw of a freighter with a double rainbow in the background and was curious on how it develops and how we as humans can visually see that with our eyes. So we have to go into the science of what we as humans are able to see with our naked eyes, and it's not a lot when it comes down to it, otherwise known as what we call the visual spectrum. Now, you've got different wavelengths of all sorts. You have gamma rays, you have infrared rays, but the colors that we know all too well, all the way from the reds, oranges, and the yellows, to the greens, the blues, and the violets. That's what we call visible light. And that is what we as humans are able to see with cones and rods in our eyes, otherwise known in our retinas. That helps us to distinguish to our brain different types of colors. So now that we know that's what we, as humans, are able to see just with our visible eyes, now we can get into why we see different types of colors, and then we can talk about how we also are able to see what we call not only a primary rainbow, but even what we call a double rainbow. So now that we've talked about the visible light, now we have to talk about a few other words. How that light can, what we call, refract, as well as reflect. Those are going to be two key words, and when we're talking about how we are visually able to see what we call a rainbow. So when you're talking about rainbows, it's in the name, rain. So usually we do need a shower, a thunderstorm, interacting with the critical angle of where the sunlight is coming in. So it all has to do with your perspective and where you're standing. But just to be able to start the process and being able to visually see what we call a rainbow, that light, it has to slow, and then it has to bend as it's entering raindrops. So once we have that process started, now we're reflecting those different colors that we can visually see at a critical angle. So when you're talking about that critical angle, that's when we start to see the reds and the violets exiting the raindrops at a different angle, otherwise known as, well, a very critical angle, because rainbows, they can come and go very, very quickly. Again, depending on where you're standing relative to the sun, and we'll talk about that in a minute, but let's go over the single reflection and the double reflection. You can think of this as a single rainbow or a primary rainbow, and then a double reflection or a double rainbow. So the single reflection is a bit more common, but when you're talking about that single internal reflection of light, usually we have a plethora of falling raindrops, and from that, this is why we see the colors in the orientation that we do. Usually you're talking about the red colors on top, and then you're talking about the violet colors on the bottom. So talking again about the single reflection, this is going to be more common, and the setup in the natural light that your brain is going to be able to see those visual colors. Remember, the primary, again, red on top, violet going to be on the bottom. So that's the primary. Now, when you're getting into the double reflection, otherwise known as what we could see as a double rainbow. Now you're talking about, with the primary, the red on top, the violet on the bottom, but for the double standard, or at least the double rainbow, those colors, well, they're switched. So now you have two reflections, and the remainder of that reflected light is going to be fainter, because you're already putting the majority of the light into the primary rainbow. But if you're able to get two reflections, you still can get what's called the double rainbow, but that second rainbow, at least visually to your eyes, is going to be a little bit more faint compared to the primary rainbow. And when you're talking about that secondary rainbow, the violets, instead, those are going to be on top, and then the reds, well, those are going to be on the bottom. So when you're talking again about the primary rainbow, reds are going to be on top, violets are going to be on the bottom. When you're talking about the double rainbow, violets are going to be on top, and then the reds, those are going to be on the bottom. So that's the difference between what we call the primary rainbow and then the double rainbow. And it all has to do with where your perspective is. Where are you viewing the rainbow? So this is very, very key in being able to just see the rainbow, or at least have a better chance of seeing the rainbow. You want to be standing between the sunlight and the raindrops, and you want to have your face away from the sun. So your back should be towards the sun, looking towards wherever we still do have rain falling. That could be in the form of a shower or a thunderstorm. And if you have that right critical angle, you could possibly see a primary rainbow, or even in some instances, a double rainbow. I'm meteorologist John Gross reporting for Beyond the Forecast.
Thanks, Sean. Now, coming up next, I'm going to take you into halos and sundogs, how they're formed, and where you can see them. We'll have that coming up right after the break. And welcome back, everyone, to Beyond the Forecast. Today, we're going to be talking about some weather phenomenon that you might see, and a lot of people always send pictures in and ask, what are these? Halos, sundogs. They're pretty cool to see, and you typically see the sundogs more so in the winter, cold portions of the seasons. Halos, you get quite a bit, still rare to see, but we get them quite a bit. And they're not just sunshine phenomenon. You also get them at night, around the moon. So how do sundogs or halos develop? Or some might even ask, what are halos and sundogs? We're going to show you. So taking a look first at what happens to create really what we see when we talk about halos and sundogs. Sunlight goes into a column or an ice crystal, column-like, for the halos. For sundogs, it's going to be more of a flat crystal, and we'll show you that here coming up in a little bit. But first off, when you have a column-like ice crystal, the beam of sunlight goes through it, and that sunlight gets dispersed. That dispersion of light gives you a spectrum of visible colors. So, sun shines into an ice crystal up in the atmosphere, and on the other side of it comes that dispersion of light, giving you the visible colors. So when you look at the sun and you have those crystals, whether it's on top or bottom, once that light goes through it, it creates that halo. Now, mind you, if you want to see this, or if you do notice the halo around the sun, don't look directly at the sun. We don't want to hurt anybody's eyes out there. But if you can put your hand up there like this person is doing here, you'll be able to see that halo around the sun. And why that halo is there is like we just described. That sunlight hits the ice crystals, and you can see disperses the light around. So you see that spectrum of light, and you get that halo. So that light refracts through the crystal, giving you that full halo around the sun. Now, it doesn't happen just with the sun. Like I mentioned before, you can see it even with the moon. So when you have a full moon on a clear, colder night, yeah, you can do this exact same thing. So pretty cool. But the angles are what matter. Think about that. So if you've ever seen the rain and sunlight was coming through and you see the rainbow, right? It all matters at where you're at to that rain and the sunshine. the angles. So the best time to see a halo around the sun is right around 22 degrees or 46 degrees above the horizon. So more in the morning or more in the evening. Pretty cool to think about. So next time the sun's out there and we do have more of the cooler conditions or maybe the high thin clouds up in the air, take a look, see if you can see the halo, because that's when you're going to have the crystals. Whether you have those high thin clouds or on a clear colder day, usually you get those crystals in the atmosphere and you'll get that halo. Now, sundogs, a little bit different, and these are pretty cool. They're kind of the quotation marks on the outside of the sun. Now, usually these are very clear, cold mornings. So a beam of sunlight goes through more of a hexagon-shaped ice crystal like this. It's flatter. But what comes out of that dispersion of light, again, is the spectrum of colors. But it's a little bit thinner. You can see it's not completely like that column crystal. It's more just kind of thin laser, if you will. But it's not going to make its way all the way around. So put this together around the sun, and you have sundogs. It looks like a little bit of a rainbow on the outside, on both sides. Those are sundogs. And you get these, again, typically on those clear, colder mornings. Pretty cool to see if you ever get up and you're like, what's that reflection going on around the sun? So best viewed right around dusk or dawn. And again, that light disperses on those bright spots on either side of the sun. Now, again, don't look directly at the sun, but you'll be able to see these quite a ways from the sun. And again, it's that sunlight going through the crystal and then refracting it into the sundogs. Pretty cool. So if you ever get the opportunity, we have them quite a bit here in northern Michigan, but you'll be able to look to someone next to you and explain the reason why. Ice crystals in the atmosphere, light going through that crystal, and then refracting, creating either a halo or some sundogs. Pretty cool for you. So there you go. Next time you're outside, check to see if you see halos or sundogs. But again, sundogs are more when it's pretty chilly out there. I'm Chief Meteorologist Michael Stevens for Beyond the Forecast. And welcome everyone to a science video for you today. Today is actually kind of more of an experiment that you can do to show refraction. So first off, all you're gonna need is a glass, see-through glass, and also a number 2 pencil. Super simple. You can use a pen, you could use a smaller glass, but make sure you can see through it because that's kind of the whole concept. So fill it up with a little bit of water. I just filled it up with half. And then take your number 2 pencil and drop it in the glass. Now, you may say, well, how is that showing refraction? Well, simple. When you get down here, it's actually pretty crazy. It looks like the pencil actually goes back and then down. It looks like a Z. The glass and the pencil don't meet up right where the water is. And that's refraction. So what's happening is you have light coming through the glass in the water, and the water is actually bending the light. Hence why the pencil looks like it's in 2 different locations. And then when you look above it, oh yeah, it's in one spot. But when you look through it, that is where you have refraction. So this is a typical case. So let's say, you're out doing whatever and you see a fish in the water, right? Well, when you're looking down, it's probably close to where it's at, but there's an angle to it because of the light coming through. Now, when you're looking down at it horizontally, you're kind of taking the majority of that refraction away. But when you're looking at it through the plane, that's where the refraction is taking place. So that is why when you're looking through something, it looks broken. And that's because the light is bending. So there you go, refraction. Cool little experiment for you to try and also explain. Pretty crazy to think that waves are going through that water and then bending what you know goes this way, but it looks completely broken. Pretty cool, huh? A little science for you. Have a wonderful day, everybody. Yes, try that out. Surprise kids, surprise your friends, and then explain to them why. Pretty cool. All right, tomorrow we will have the live streaming Beyond the Forecast podcast for you, 10 in the morning on the 910 News Facebook and YouTube channel, talking about the latest weather that we've had this past week. But thank you for joining us. Do appreciate it. I'm Chief Meteorologist Michael Stevens for Meteorologist John Gross, Meteorologist Haley Fischetti. Be good, stay safe, take care. We'll see you all tomorrow for more Beyond the Forecast. Bye, everybody.